Okay, so we're ready for hypothesis tests now, and the setup for this is as follows. So given a population model, and let's suppose that we just have a couple of x's in our population model, we collect data for x1, x2, and y, so these go into our spreadsheet, and then we use the regression commands, which we know now are ordinary least squares computations, to obtain estimates of alpha 0, alpha 1, and alpha 2. Estimated coefficients are denoted with these hats above them, and if there are no hats, as we have here, those are the true unknown population values. So these are unknown, and these are known because we actually obtained them via estimation. Suppose that we hypothesize that there is a positive relationship between alpha 1 and between x1 and y. That would translate into a positive number for alpha 1. So if alpha 1 is positive, it means that when x goes up, on average, y goes up. If x goes down, y goes down. So they move together. And let's suppose that this is our a priori belief. Okay, this is our hypothesis after we've conducted our theorizing and so on. How will we decide whether this is a true statement or a false statement? That's really what we want to get at. And then secondly, what can we say about the reliability of our conclusion? Okay? So every hypothesis test begins with a formal hypothesis. And the way we conduct these formal hypotheses is to write down what we call the null hypothesis, okay, and the alternative hypothesis. Alternatives are either designated as H1 and sometimes you'll see HA, okay? And this HO is really the null hypothesis, meaning it's typically the result that we don't believe, okay? And typically the result that we believe is in the alternative. And we'll explain why a little bit later. So our a priori belief goes in the alternative. In this case, that means alpha 1 greater than 0. And these hypotheses, when we put them together, have to be complete. So if our a priori belief is that alpha 1 is greater than 0, alpha 1 less than or equal to 0 must be in the null hypothesis. So we don't believe this. Okay. So this is a formal statement of a hypothesis. Typically in an academic paper you will not see the formal hypothesis laid out like we have it here, but it underlies what's going on. We're thinking about the existence of this hypothesis, but as you learn how to apply the statistical technique, you need to get in the habit of writing out the null and the alternative formally. This is called a one-tailed test, and you'll see why in a second. Anytime we have an inequality in the statement in the alternative here, it's going to be called a one-tailed test. So I want you to stop for a moment and think about what evidence you would take as acceptable to conclude that the alternative hypothesis is actually true. At the moment, you're probably thinking that we're going to estimate our model, we're going to obtain an alpha 1 hat value, and the alpha 1 hat value will be taken as evidence that we will use to accept or reject our null hypothesis. Okay, we typically talk about the null as rejecting the null or failing to reject the null. So is alpha 1 hat going to be sufficient evidence to reject HO in favor of our pet theory, that which we believe in the alternative? Okay, that's the question mark. So that's probably what you're thinking, and that's a good way to start this process conceptually. We're going to see later that this isn't going to work. But I will tell you that this is the concept that we're trying to develop. By the classical assumptions, we know that if we were to repeatedly gather samples from a given population and we were to repeatedly estimate our model and collect all of those values of alpha 1 hat that we obtained, and plot them in a probability distribution, that if we had enough of those samples, it should approximate this normal curve. And it should approximate the normal curve because the y's are normal, and the y's are normal because the epsilons are normal, okay? We also know that the true value, if we have an unbiased estimator, the true value of alpha 1 should be the mean, okay? Now I've picked 0 here, and I've picked 0 specifically because it's the dividing line between our null and our alternative hypotheses. So if you'll recall, we had a null hypothesis that said alpha 1 less than equal to 0, and an alternative that said alpha 1 greater than 0, right? So two things we can observe. One is this 0 is in fact contained in the null hypothesis. So if our null hypothesis is true, 0 could be the true value, right? And the dividing line between the null and the alternative is 0. And so typically what we're going to put here in the middle is a value for alpha 1, okay, that is A, consistent with the null, and B, as close to the alternative as it can be, okay? So 0 is that number. But we're imagining that this is a true alpha 1 value if the null is true, okay? Well, we'll talk more about that later. But now let's look at what evidence we would accept generally to conclude that alpha 1 is bigger than 0. Well, probably you would say that if we have a sufficiently large, okay, if we have a sufficiently large, speaking loosely, alpha 1 hat, we're going to conclude alpha 1 is greater than 0, right? Speaking loosely, that's probably the way we're going to think about it. So what does sufficiently large mean? Well, we're going to pick some threshold value. Okay, let's call it alpha critical, right? And if we draw an alpha 1 hat in this region, then we will reject HO. If we draw an alpha 1 hat, we will fail to reject HO if it's in this larger region right here. We would, based on this critical value, this threshold value, this definition of what sufficiently large means, we would call this the rejection region. Okay? We would call that the rejection region. So ideally, that's what we would do, okay? There's one problem with this approach, and the problem with this approach is that we don't yet know how to evaluate the reliability of our conclusion. So we're going to either conclude that alpha 1 is bigger than 0 based on an alpha 1 hat being in this region, or we're going to conclude that alpha 1 is less than or equal to 0 if we get an alpha 1 hat down here, but we don't know how to reliably assess whether that was a good conclusion or not. So that will be the next step in figuring this process out.